Welcome to Mechanics of Materials first live class. Okay, so for this current semester, I'm waiting for the participants to join. Meanwhile, I thought I will clarify one of the questions that was raised in the question form that was shared. The question was whether stress and strain, which is first, whether the stress comes first and then that induces a strain, or whether the strain comes first and then that induces the stress. To phrase it differently, it's like asking whether the chick came first or the egg came first. Okay, but it's not like that in this case. Stress and strain are what are called as simultaneous events. Okay, we say that two events are simultaneous if they occur at the same instant in time. Okay, so stress and strain occurs at the same instant in time. Okay, it is not that one is causing other. It's not like you turn on the switch and the light glows. The electricity flows from the switch to the light, and it is not a cause-effect relationship. Okay, it is not like a cause-effect relationship. It is a simultaneous relationship. Okay, so that's what I want to say first. The second question was whether stress and strain are synonymous. Okay, are they same? That was another question that was asked. And the stress and strain are not same always. They are same in case of elastic bodies, or in a body when a body undergoes a elastic deformation. The stress and strain can be considered to be same. Okay, so why is that? The stress and strain are related linearly or non-linearly in a one-to-one fashion for elastic bodies, right? So what that means is, if I give a strain, you can compute what the stress in the body is, or if given a stress, you can compute what the strain in the body is. Okay, that is the reason for elastic bodies, the stress and strain are synonymous. Whereas if the body undergoes a plastic deformation or an inelastic deformation in general, or a viscoelastic deformation, then it will depend upon the history of the loading or history of the straining of the body. That is, the stress is not dependent only on the strain at the current instant in time. It depends upon the entire history that the strain has been, the body has been subjected to. Okay, the historical strain that the body has been subjected to will influence the stress at the current instant in time. Okay, for this reason, you can't relate stress and strain directly. It is given a strain value, I can't tell you what the stress is. The stress can be any value depending upon what the historical strains that the body has been subjected to. Okay, so in these bodies, namely plastic, viscoelastic, viscoplastic bodies or processes, the stress and strain are not the same. They are different. Okay, and hence you have to be careful when you use stress and when you use strain. Stress is a kinetic quantity, strain is a kinematic quantity. Okay, so you have to be careful what you are referring to when you talk about, and you can't say stress and strain in a synonymous, use stress and strain in a synonymous fashion. Okay, so these were the clarification that I want to give at the beginning of this session. So I'm waiting for people to join in to clarify their questions that you might have. So I'll write the two questions that we are looked at in this session. Okay, the questions we looked at first was, does stress cause strain or strain causes the stress? Answer is stress and strain are not related by cause effect relationship, but are simultaneous events. That is, one doesn't cause the other, they are simultaneous events. Okay. Second question we answered was, is stress and strain synonymous? Answer is not in general. It is so only for elastic process. Okay. Okay. Okay, there was a question in the forum on the sign convention for the stresses, which I thought I will explain it in the live session. Okay. Share the screen. Okay. So the question is, we normally take tension as positive and compression as negative, right? So is that an assumption, or is it the sign convention, or is it like that? Naturally is the question. Okay. Third question we are addressing is tension positive and compression negative, an assumption. Or is it a consequence? Or is it a consequence? Answer is it is a consequence of right-handed system that we follow. Consequence of right-handed coordinate system. Okay, let me explain why. Now, let's draw first the coordinate system. Let's say this X, Y, and Z. Okay. Now, for this is a right-handed coordinate system, right? When I curl my fingers, what happens? The thumb points the Z direction, right? Right hand, if I curl, thumb points the Z direction from X to Y. The thumb points the Z direction. So it's a right-handed coordinate system. Now, for this, if I draw a stress cube in this coordinate system, if I draw a stress cube, okay, I've drawn a stress cube. The origin might be at the center of this cube, or whatever, it doesn't matter now for discussion. Okay, so now what happens? This face in here, as a normal EX, right? This has a normal EX. Since this has a normal EX, according to our definition of attraction, T's of EX would be what? Sigma transpose times N, right? That is, if I write it in matrix form, be sigma XX, sigma XY, sigma XZ, sigma YX. I'm not assuming it's a symmetric tensor. Sigma YY, sigma YZ, sigma ZX, sigma ZY, sigma ZZ into EX is 1, 0, 0. Right? Here, what do I get? I get a positive sigma XX EX plus sigma YX EY plus sigma ZX EZ. Is this right? No, because I have to put a transpose in here. So if I put a transpose in there, this index will be other way around, right? Because I have to take the transpose of that matrix. So this is going to be XY, XZ. Okay. That is why we write it as sigma transpose N. Okay. This is a sigma matrix. Sigma transpose N would be like that. Okay. Now, what happens here? If sigma axis is positive, what will be its direction? sigma x is positive means it will be in the direction of Ex. So sigma xx positive means it is going to be in the direction of Ex. This is sigma xx. Sigma xy is positive means it is going to be in the direction of Ey, which is that. So this is going to be sigma xy, and this is going to be sigma xz. Right? Now, if I were to look at the normal on the other face, what will happen? Normal on the other face is t is of minus 1, right? Normal on this face is, this normal is minus Ex. So I will add t is of minus Ex would be all this with a negative sign, right? Minus sigma xx Ex minus sigma xy Ey minus sigma xz Ez. Okay. So now what will happen then is my sigma xx direction, sigma xx is positive. This is the negative Ex direction. So the positive sigma xx on this face, okay, on this face would be yeah, this is going to be sigma xx, this is going to be sigma xy, and this is going to be sigma xz, right? Okay. So now what happens? Now you see that naturally, if I assume sigma xx is positive, then what happens is tension becomes positive. Sigma xx alone, if I draw the sigma xx alone on these two faces, if I draw the sigma xx alone, what is happening? On this face, sigma xx is like this, and on this face, positive sigma xx is like this. What is this? This is a tensile state of stress. I didn't assume tensile is positive, but I get it as a consequence of right-handed coordinate system. Okay. Similarly, what happens if I look at sigma xy? This is sigma xy, and on this face, the sigma xy is this. This is sigma xy, right? Now, what happens? This produces a anticlockwise moment, right? This produces an anticlockwise moment. Sigma xy produces an anticlockwise moment. Okay. Since it produces an anticlockwise moment, this shear direction is positive. Okay. The shear that produces an anticlockwise moment is considered to be positive. Okay. On the other hand, to balance this, what will be the shear, complementary shear on top and bottom faces? There will be a clockwise, that will produce a clockwise moment. But again, the direction of shear is fixed. On this face, it is going to be on the top, and on this face, it is going to be on the bottom direction, and this is the positive shear, not the other way around. Okay. In courts of practice, because of traditional reasons, they will assume an opposite direction for the positive shear direction. When you draw the shear force, they will assume that this to be acting down and this to be acting up, because that is how the reaction of simply supported beam would be. The shear force distribution of simply supported beam would be that they will take it as a positive shear direction. But that was an assumption. But it need not be an assumption if you follow rigorously vector mechanics. Okay, this is a consequence of a right-handed coordinate system that we are following to uh, represent the problem. Okay, okay. So, any questions? Any questions from the participants? Okay, there's a question on what is meant by plane stress. Okay. Fourth question is, what is meant by plane stress? Typical textbook definitions would be one row and one column to be 0. That is, if sigma is of the form A, B, B, C, 0, 0, 0, 0, 0, 0, this is called as a plane stress. But the correct definition for a plane stress is determinant of sigma must be 0. Okay, what happens? Why is this the correct definition? Let me look at a stress state. Sigma is given by 10, 10, 10, 10, 10, and 10. What is the determinant of this? This will be 0. All the rows and columns are same. So if you take a determinant, it will be 0. What is trace of sigma? That will be 30. And you can show that the second invariant is also 0. That is K2, which is trace sigma square minus trace of sigma whole square into 1/2 will also be 0. Okay, will also be 0. You can compute that and see. So this is an example of a uniaxial state of stress. Okay, that is, in some other coordinate system, I can represent this stress sigma u. Let me say, I can represent sigma u as 30, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, this is an equivalent representation. Both this and this are equivalent representations of the same stress state. We have seen that you can transform the stresses, right? So when I transform it to a different coordinate system, you'll find that this stress state and this stress state are the same. So this idea that one of the rows and one of the columns has to be 0 for a plane stress, though is right, it's not a necessary condition. It's a sufficient condition to say that it is a plane stress state. The necessary and sufficient condition to say whether a state of stress is plane or state of strain is plane is determinant of that matrix has to be 0. So this is the definition of plane stress. Okay. Any other questions? A related question here is, why do we need these definitions of plane stress, uniaxial stress, and all those things? Okay, it's convenience. So basically, if determinant of sigma is 0, there will be a representation in some form wherein I can write it as AB0, BC0, 0, 0, 0. Okay, so in that case, what will happen is I can solve the problem easily. I don't have to worry about 6 components of stresses. I need to worry only about 3 components of stresses. That's why we harp upon what is a plane stress, whether a body can be modeled as a plane stress and so on, or a plane strain problem and so on. Okay. Any other questions? Okay. Wait for a couple of minutes to see if others are joining. If not, we'll wind up the session. Okay, there's a question on the difference between true strain and engineering strain. Let's see that. Okay. Fifth question is difference between true and engineering strain. Okay. So what is the engineering strain? Loosely, engineering strain is defined as change in length by original length. Okay, what will that be? That will be length in the reference minus, or rather, sorry, length in the current configuration minus length in the reference configuration by length in the reference configuration. Okay, what is this? This will be lambda of n minus 1. What is lambda of n? Lambda of n is length in the current by length in the reference along the direction n. Okay, that is the definition of engineering strain. True strain, on the other hand, is change in length by current length. Okay, that will be nothing but L current minus L reference divided by L current. Okay, that will be 1 minus L reference by L current. That will be 1 minus 1 by lambda of n. If I use the same definition of lambda as in here. Okay, so this is true strain. Okay, but if I were to view it as infinitesimal strain and the infinitesimal strain being incremented at each load increment and so on, this can be approximated as ln of lambda n. Okay, what is the Taylor series expression of ln natural logarithm of x or something like that? It will be x at 0 will be 1 minus differentiation of this 1 by x. Okay, so minus you can show that if you do a Taylor series expansion of this as ln 1 plus epsilon, okay, where lambda n is 1 plus epsilon n. Sorry, give me a minute. I'm dealing only with scalars here. 1 plus epsilon n, where epsilon n is the strain. Okay, this will be 1 minus epsilon n. Okay, roughly. That is 1 by lambda n is 1 minus 1 plus epsilon. If I write it there, 1 minus 1 by 1 plus epsilon n, and if I do a Taylor series expression, that will be epsilon n. Right? Okay. Same thing with ln of 1 plus epsilon n. If I expand it, it is going to be ln 1, which is 0, and this is going to be epsilon n. Sorry. This is going to be epsilon n. Okay. So, both 1 minus 1 by lambda n and ln of lambda n are two different forms of a true strain. Okay. Wherein what you say there is the change in length by the current length instead of the original length. These definition of strain won't make a difference if the change in length is small. On the other hand, if the change in length is large, then these two definitions will make a difference. To give an example, let me say that delta L was 10 power minus 3. Okay, then what will happen? The first case, the engineering strain is, and the initial length was 1, say, is going to be 10 power minus 3 by 1, and true strain is going to be 10 power minus 3 by 1 plus 10 power minus 3. This will roughly evaluate to 10 power minus 3 again. Okay. On the other hand, if my L is still 1, but delta L is also 1, say, what will this be? Engineering strain will be 1 by 1, and the true strain is going to be 1 by 2, half. So what was nearly same becomes an error of 100% depending upon what measure of strain you use. That's why strain is not a fundamental measure. Whereas the stretch ratios, these quantities which are called as stretch ratio, is a fundamental measure of the deformation or the relative deformation that the body is undergoing. Okay, so you have to always base your theory on the stretch ratio, and strain is something you derive from it depending upon the convenience. First level course, you don't distinguish between engineering strain and true strain because the strains are small. You are focused on small deformations. Okay, so you don't make a difference between the two. Okay, any other questions? Hope this is clear. Any other questions? I didn't follow the question. Is there any relationship between them? Engineering strain. Okay, you are asking, is there any relationship between engineering strain and true strain? Is it? There is. I gave the relationships in the thing itself, right? Okay. So the engineering strain is as shown here. It will be 1 lambda n minus 1, and this is 1 minus 1 by lambda n. Okay, so lambda n is a common factor between the two, so you can rewrite it, and you can substitute for lambda n from the true strain to the engineering strain or vice versa, and you can relate the two. Okay, there's an exercise in algebra. Okay, I'll just give the end result. Okay, from the first equation, I have lambda of n is epsilon engineering plus 1, say. Okay, and from the true strain, epsilon true would be 1 minus 1 by 1 plus epsilon engineering, which will roughly be epsilon engineering if epsilon engineering is small. Otherwise, it won't be the case. Okay, I can rewrite it as epsilon engineering by 1 plus epsilon engineering, epsilon true strain. So this is the relationship between the two, and you can go from one to the other. If the epsilon engineering is small, then you can see that it will be epsilon engineering itself. On the other hand, if it's large, it will be different. Okay, that is using this measure for true strain. On the other hand, if I use the logarithmic strain for the true strain, then there'll be a different relationship in here. It will be this. It will be this relationship. Okay, why this is engineering. Okay. Hope that helps. Any other questions? Any other questions? How to draw shear force diagram and bending moment diagrams. Okay. Okay. What question number is it? 3, 4. Okay, sixth question is how to draw shear force diagram and bending moment diagram. Okay, what is the relationship between shear force, bending force, and the applied load? You know that dm by dx plus v is 0 and dv by dx plus q is 0, where shear force is represented by v and bending moment is represented by m, and q is the applied loading. Applied loading, distributed load, right? Okay, so what you do, first you draw the shear force diagram such that since you know the applied loading, it will be one order greater than the applied loading, and the slope of the shear force diagram should be the magnitude of the applied loading at that point where you are drawing the shear force diagram. To illustrate that with an example, let me consider a cantilever beam, okay, subjected to a triangular load like this. This is a classical question that will come in many of the interviews or exams. Okay. So now you will be asked to infer what is the shear force diagram and bending moment diagram. Now what happens at the free point? The shear force is 0. Only as a suppose there will be shear force. So you know that shear force has to be 0 here, and maximum value which will be the total load W in there. Okay. And since the load, I explained a little while ago on a sign convention that this will be a negative shear. So this is going to be a negative shear like this. So it can be like this. Is it a straight line? Classical question is, this is a straight line. Second option is parabolic like this. This is a parabola. Maximum here, minimum here, slope is 0 here, whereas slope is maximum here. And the third option would be again a parabola, but not it will be a parabola like this. Maximum here. This is also a parabola. So which one is right? we know that this has to be 0 here and maximum here, but I have three different lines connecting them. Since Q is linearly varying, what will happen is, if I integrate that, I'll get a quadratic function. So from basic calculus, you know that if Q is linear, it varies as ax plus b, then b will be ax square plus bx plus c. So it is going to be a parabola. Now, which of these parabolas will choose, blue or the red? The correct answer is the red, because the slope of dv by dx, that is the slope of this curve, should be equal to the magnitude of the applied loading there. Okay. Here it has a finite slope. Here it has a finite slope. This is theta. Okay, that is dv by dx. This is dv by dx. And you can see that there is a value here for q. It is not 0. The q has a value. So this dv by dx will be equal to the q at x equal to L. Okay. Whereas here the slope is horizontal. dv by dx is 0. Which means q has to be 0. Is q 0 here? Yeah, it is 0 here. This q is 0. And then this is the right variation for the shear force diagram. Okay. So the points to be noted when you draw shear force diagrams are 2 or 3 things. One is, will there be a shear force of some magnitude at a given point, at the boundary points? If it is a suppose, there will be shear force. If it is a free end, there won't be shear force. And from there you mark whether it is 0 or non-zero. Then you find what is the order of the shear force curve by integrating the applied loading, okay, from calculus. So you decide whether it's a straight line, whether it's a parabola, whether it's a cubic function, and so on. And then what you do is you decide on, based on the slope of the shear force diagram, whether it should be, if it is a parabola, whether it should be a parabola like this or a parabola like this. Okay. So that's how you decide on how to draw the shear force diagram. Coming to bending moment diagram for the same thing, which one is right? Dm by dx is v. V was a quadratic function. So what will happen? The parabola will now become a cubic function as far as the bending moment goes. This is for a shear force, and this will be cubic for bending moment. I'm not redrawing the curve, I'm just writing it again. Shear force, and this will be cubic for a bending moment diagram. Okay. So what will happen now? Which one is right, blue or the red? Now the blue is the right thing for the bending moment, because shear force is 0 here. At the support, the shear force is 0. Okay. At the support, the shear force is 0. And hence, what will happen is, the slope of the bending moment diagram has to go to 0. Whereas here there's a shear force, and hence the slope of the shear force diagram will not be 0 here. Okay. The bending moment diagram will not be 0 here. Slope of the bending moment diagram should not be 0 at the support here. Okay. That's how you decide on how to draw the bending moment diagram and shear force diagrams. You first take the loading, integrate it, find the order of the equation, see where the magnitude of load goes to 0, there the slope of the shear force diagrams has to go to 0. Integrate the shear force diagram, get the bending moment diagram, find the order of the equation, and then you figure out whether the slope of the bending moment diagram is 0 or non-zero, depending upon whether the shear force is 0 or non-zero at a particular point. Okay. And another point is, if the shear force is 0, the bending moment will be maximum at that point. Okay, except for a cantilever beam. If it is a simply supported beam, and now the shear force is 0, the bending moment diagram will be maximum at that point, because dm by dx is 0 represents the extremum of the bending moment diagram. Okay, that's how you figure out on the bending moment and the shear force diagrams. Okay. Any other questions? Any other questions? Okay, as a question on how to draw the Mohs circle. Seven Mohs circle. Okay, so what is the axis of the Mohs circle? The axis of the Mohs circle would be, what would be the x-axis? X-axis is going to be the normal stresses sigma n, and y-axis is going to be tau's of n. Typically, this will be written as sigma xx or sigma yy, which is the incorrect notation. It can be both. Both doesn't mean the same thing, but it is the normal stress is the right way to represent that axis, and this will be the shear stress. In a plane stress case, this will be sigma xy. Okay. Now, you know that Mohs circle, what we are drawing is for a plane state of stress, plane stress state. For a plane stress state, I can write the stress as sigma xx, sigma xy, 0, sigma xy, sigma yy, 0, 0, 0, 0. And I know that trace of sigma xx, trace of sigma now is going to be sigma xx plus sigma yy. This doesn't change depending upon the coordinate coordinates used to represent the stress tensor, right? So this point, which doesn't change depending upon the coordinate that is used to represent the stress tensor, will be the center of the circle. Okay, sigma xx plus sigma yy by 2. This by 2, this let's say k1, then k1 by 2 will be the center of Mohs circle, because the center cannot change with the component changes as the component change as you go along for different orientation of the coordinate system, right? So that is the center of the Mohs circle. Okay. Now, then what will happen? Let's assume for illustration, sigma xx is greater than sigma yy. Okay. Then where will be sigma xx? Sigma x is greater than sigma yy, so it is going to be greater than the mean. Sigma x is going to be some point here. It's going to be sigma xx, and this point is going to be sigma yy. It will be lesser than the mean. Okay. Now I have tau xy or sigma xy also, right? The question is, where should tau xy be? And I'm assuming that both of them are greater than 0 also in this case, in the illustration. Okay. Now tau xy, what will happen? Should I draw it on the above the axis or below the axis? The question. Tau xy will be above the axis because that is a positive shear stress. I am assuming sigma xy is also positive. If I assume it as positive, at sigma xx it will be above. Okay. At sigma yy point is going to be below. Okay. And then I draw this. Then I join these two by a line. Okay. This is sigma xy. And same thing here. This is sigma xy. Okay. Now I got the center, I got the radius, these 2 points are on the circle, so I can complete the circle now. Okay. There used to be a circle here. Okay, I'll draw it. Okay, there's going to be a circle in here. Didn't come properly. Okay. That looks like a circle, but not on the point. Okay, you have to take it as a circle. Okay. So this completes the Mohr circle. So these will be the principal stresses. This and this will be the maximum principal stress sigma 1. This will be the minimum principal stress sigma 2. Okay. The maximum shear stress would be the radius. This will be tau max. That will be tau max. Okay. So from here you can say that tau max is radius of the circle, which will be root of sigma xy square plus this distance. What is that distance? That distance would be sigma xx minus sigma yy by 2 the whole square. Because it is sigma xx plus sigma yy by 2 minus sigma xx. Okay. So that will be, since I'm squaring where the minus sign doesn't matter. Okay. And then I can say that sigma 1 would be sigma xx plus sigma yy by 2 plus r, and sigma 2 would be sigma xx plus sigma yy by 2 minus r. So you have found all the relevant things in the Mohr circle. Okay. So I hope this helped you on how to draw the Mohr circle. Even if sigma xx is lesser than sigma yy, tau xy, if it is positive, should be always up on the sigma xx location. Okay. On sigma yy location will be down. That's because when I rotate the coordinate system by 90 degrees, that's the sign of the shear stress will flip. That's why it is like that. If you view it as a normal stress, sigma xx and sigma xy are the stresses in the same plane. We saw before, right? Sigma xx and sigma xy are the stresses on the same plane. Okay. So if both are positive, they'll be on the same direction. Okay, in the same plane. Okay. So that's why we are harping upon the point that wherever sigma xx is there, if sigma xy is positive, it will be on the positive direction of the shear stress axis. Okay. Okay. Hope it helps. Any other questions? Okay, if there are no more questions, we'll wind up for the day. Thank you for all those who are able to join this live session of mechanics of materials. Next live section of mechanics of materials will be in the last week of September. The announcement will be posted on the website. Okay. Thank you. Thank you.